Okay, let's start. Good morning and welcome back. We were discussing about MOSFET and its current voltage equations under various regimes. So, for this N-channel MOSFET or N-MOSFET, we derived that the current between drain to source, right? We can break it up into multiple regimes. So the first one is under the condition that if VGS is less than a certain threshold voltage, my IDS will be equal to 0. However, if VGS is now greater than threshold voltage, greater than or equal to threshold voltage, I have to worry about two things. What are the two things? There are two regions of operation when the transistor is on. What are those? Linear and saturation, right? So you can have linear or triode region, and another is saturation region. And in linear region, the current voltage equation is saturation region is this. So the key takeaway from this, the key difference between these two regions, linear and saturation, is the fact that in linear region, you have a dependence on the drain to source voltage, on the current between drain and source, right? So when you have a dependence of current between the ports, when the current between a port, current through a port depends on the voltage across the port, which means there is a resistive behavior, right? So this naturally means that when you are in linear region, you will have some sort of resistive behavior, and the MOSFET at the output terminals, other between the drain and source, will behave like a resistance to some extent, right? So this is not a linear resistance that you can appreciate, because had it been a linear resistance, this VDS squared term wouldn't have appeared. But since this is, it's a nonlinear relationship between I and V, which essentially means that I can probably, in a small signal regime, in a small signal approximation, I can approximate this as an incremental resistor when the increment is related to the increment of VDS with increment of IDS. Now, turning our attention to the current voltage equation in the saturation region, there we see that there is no dependence of the current on VDS, right? So you have these terminals. Let's say this is a black box. You didn't know anything. Let me call this VD. Let me call this VS. And you are applying a voltage VDS, and you are observing this current IDS. What will you observe? You will observe that this current doesn't change even if I change VDS, right? The current doesn't change even if I apply a voltage source and try to change the voltage. And what does this, what does this remind you of? Y22 equal to 0, great. But in terms of, is it like a voltage source? Is it a resistor, current source? It's a current source, right? Exactly, right? So you have it appears to be a current source. It appears to be a current source through its output terminals, because you are applying, you are trying to change you are changing the voltage, but you are not seeing its effect in any change of current. This is the characteristics of an ideal current source. And this should not surprise us, because the relationship or the plot between IDS and VDS was something like this, where naturally here in this region you are seeing, IDS kind of a strong dependence on IDS, strong dependence of VDS on IDS, and in this regime you are not seeing any dependence of VDS on IDS. So which essentially means that here my device is behaving like a current source, and here my device is behaving like a resistor. But the key takeaway from this discussion is the fact that these current sources or resistors are voltage controlled, right? These are the value of the current is dependent on the voltage of some other terminal. It's a dependent current source. It's a voltage controlled current source. It's a voltage controlled current source or VCCS. If you are operating the transistor in a saturation region, and this is a voltage controlled resistor if you are operating it in the triode region. Okay, so now, I mean, naturally, when you have some new device at play, which can give you some controlling features, which means you can potentially use it to design many more circuits, right? Because you started off with resistors, capacitors, inductors, voltage sources, current sources, but all those didn't have any controlling terminal. Here you have a controlling terminal. Moment you have some controlling terminal, which means you can play around with it, right? And that's what we will do from now on. Okay. So now, recall that why are we doing all these things? We are essentially doing all these things because ultimately our goal is to make an amplifier. Okay. So now how do we make an amplifier? So let's start off with this vanilla in MOSFET. By the way, one more clarification, not a clarification, one more addition, that forget about the term. Vanilla means, okay, I mean, okay, depends, somebody likes vanilla. Okay, so okay, so okay, forget about what I said there. So this flavor of MOSFET is we call this enhancement type in MOSFET if threshold voltage is greater than 0. So for if VTH is greater than 0, we call this enhancement type MOSFET. Right? And all the arguments that I had laid out till now was based on the fact that VTH was greater than 0, right? You had to apply a voltage. You had to apply a voltage between VGS and body, or VG and body, or VG and VS in order to develop that channel, right? You had to induce electrons underneath the oxide in the channel so that the electrons can be pushed by applying VDS. So inherent assumption there was that you had to apply a positive voltage in order to develop the channel. But as it turns out, it need not necessarily be the case. You can make some MOSFETs where at 0 voltage itself, the channel exists. Those type of MOSFETs, in this course, we will be essentially dealing with this enhancement type MOSFET because that is of more use to us. The reason is as follows. So let's say that you have this MOSFET where threshold voltage is -1 volt. Okay, what does it essentially mean? It means that if you apply a 0 voltage, if VGS is 0, you still will have channel charge, which means if you apply a VD and VF, there will be current. Right? That's all it means, threshold voltage of negative. Now, threshold voltage of negative might seem okay for some application, but it is definitely not okay if you are trying to make a switch out of the MOSFET. Right? So what is a switch? So let's say you are trying to make a switch, you apply a voltage between these terminals of the switch, and you have a controlling terminal here. Let me call it V. And you would expect that if I set VS to 0, I should get infinite resistance between VD and VS. And if I set VS to some, this should not be VS, right? This should be VS. So V control, let's say. If I set V control to a high value, this switch should act like a short circuit. right? So that's what a switch is. You turn it on, it should pass. If you turn it off, you obstruct the flow. Now, what is turning on and turning off in electrical parlance? In electrical parlance, we say that if we apply zero volt, which means that is the minimum I can go, I'm turning it off. Then if I turn it on, which means I apply V control to be higher than zero, then I'm turning it on. So naturally, you can see that a MOSFET can be used as a switch. Not this example, but if a MOSFET with threshold voltage more than 0 volts can be used as a switch. But if the threshold voltage itself is negative, which means you are never able to turn off the MOSFET, right? Which means that you would lose that application. And as it turns out, when you will take 370 and some applications, I mean, some examples you have already seen in ESC 201, digital logic is nothing but a switching logic, right? So it's all about ones and zeros, which means essentially you are trying to make a switch out of it. I mean, rather you are using switch to make digital logic out of it. So if your threshold voltage is always negative, which means you cannot get to zero ever, which means you cannot use it as a you cannot use it for any digital purposes. And as it turns out, most of your devices which use, I mean, almost all of your devices which has a microcontroller inside, right? You will have a microprocessor inside, a DSP inside, and they are essentially operations of switch. They are all binary operations. They are operations of switch, which means you would want an application. You would want to ensure that this switching operation helps you to realize what you want. There is one more aspect to it that one might argue that, hey, I mean, okay, if I am not able to turn off a switch, that is also fine. But as long as I am within a range of voltage, I can demarcate this is 1 and that is 0. But the issue with that is, if you are not able to turn it off any further, there will always be a current between drain and source, right? If you are not able to turn off the channel charge and you are still applying a VDS, there will be a current, and that current is essentially a loss. If you would like to turn off a switch, you would want that there is no power consumption through a switch, right? So, for example, if I set V control to 0, I would expect this current to go to 0, right? Because if the current is not equal to 0, this is not serving any purpose, right? It's essentially a loss. So that is why this enhanced, I mean, these type of MOSFETs, I think this is called depletion type MOSFET. I might be wrong in the terminology, but that type of MOSFET is not used very often in circuit design. We mostly limit ourselves to MOSFETs which have threshold voltage of greater than 0, which are called enhancement type MOSFETs. Okay. Yes.
So why is this negative voltage a problem for us?
No, you cannot do that. His question is, why is it a problem? Because we could, I could as well reverse the terminals of VDS or VSG, right? Yes. VSG, right? So you're saying I can as well reverse the terminals between this, right? And possibly it can stop it, right? But note that ultimately you would want the source terminal is common between drain and between the gate and source and drain and source. So if you are planning to turn it off, which essentially there are two implications of that. You are essentially saying I am fixing this, I'm fixing this terminal and I am moving this. But if I have to move V control to turn it off, which means I have to go negative, right? So the only other option is, let's assume I fix V control and I move VS. So now if you are moving VS, then you are limiting your options. You can only play around with VD, right? So in principle, what you are saying is right, but it seriously limits your option. Okay. So his question, did you understand his question? Okay, let me repeat. His question was, why should I limit myself to applying a voltage between VGS to be greater than 0? I can as well flip it and say that VSG can be greater than 0. That is equivalent to saying applying a negative VGS, right? So the whole problem is because we don't know how to apply a negative voltage. 0 is the minimum I can apply. So let's assume that I set V control to 0, right? And I want to turn the MOSFET off. then what should I do? I have to increase Vs, right? Fine, MOSFET is turned off, but then what happens? You have some logic connected to VD, some network connected to VD. However, now you would want to also have some network connected to VS also, because more options, right? You would want to have access to both these terminals. But because you are using VS to turn off and on your MOSFET, you are limiting your options. No, so let's say you have a switch here. You would want to connect something here, you have to connect something here. And these logics should be independent of whether you are turning on the switch on and off, right? But if you have to access this terminal to some fixed voltage to turn it off, which means whatever the logic you have here is dependent on whether you have to turn the switch off and on, right? So essentially permutation combinations, you have limited options, right? This is one of the ways of explaining it. Okay, so now you will learn about these things in 370. So that's a digital design course. We deal with it in detail in that course. So anyhow, so now that threshold voltage is positive for all the MOSFETs in this course. So now the question is, how do I get to getting amplification? So assuming that it has been biased in saturation, my small signal equivalent is, this is V1. This is Y21, which is equal to, now we'll call it as GM. And this is my incremental equivalent of the MOSFET. Okay. So, and incrementally, we know that if I apply a VI here, let's say this is source resistance, and I have a GM here, this will, we have to set up the MOSFET in such a way that it behaves like the stuff inside the box in the incremental sense. So now the question is, how do I set it up? Because when I am sketching the incremental equivalent like this, I'm assuming that the overall MOSFET is a saturation region of operation. So now tell me, how would you set it up to get to saturation region operation? So you have a MOSFET. I would want to bias it in saturation. So what is the first thing you need to do? Firstly, it has to be on, right? That is the bare minimum. Yeah, you need to give a threshold. You need to give a voltage which is more than the threshold voltage between the gate and the source terminals, right? So how do I do that? I apply a voltage source between, let's say, the gate and the source. And this, let's call this VGSQ. And VGSQ has to be greater than threshold voltage. Fine, the transistor is on. But we'll have to also ensure that the transistor is in saturation. So what should I do? By the way, I mean, let's say that you are in the lab and you have set up the circuit like this, whatever you are seeing here. Only VGS, let's say threshold voltage is 1 volt. And you have applied a VGSQ of 2 volt. So what is the condition? What is the operating regime of this transistor? This is what you have.
Basically, we need to have this VGS,
No. So you have applied VGSQ equal to 2 volt. Okay. No connection. This is what it is. Okay, it will not work, but there will be a region of operation. Is it in cutoff?
Yes.
How many of you think it's in cutoff? How many of you think it's not in cutoff? The question is, whatever you see here, right? Whatever you see here, this is all you have. You have set it up like this in the lab. What you change is the region of operation of this MOSFET. When the VDS, right? It's the source is down, it is open. Yes? Cut off. How many of you think it's cut off? Okay. But how rest of you? Cut off. Okay. Anybody who thinks it's not in cut off? Why? Anybody can volunteer?
There is charge,
Where?
like capacitor, there is charge.
There is a charge here, right? Because it's above threshold voltage. I have applied a VG which is above threshold voltage.
But charge is a part.
I know charge, with the charge needs a path to flow. When current it flows, you have a current. But whether it's in on or off, does it depend on whether you have a current or not? It doesn't, right? So remember, recall the way we introduced this MOS structure. You had a capacitor and you have a P minus. You applied a voltage here and you developed some channel charge. We were not into any current flow, but the transistor was, this structure was on. So you will have channel charge here, but the channel charge is not moving. But you will have channel charge, which means the transistor is on. Do you agree?
Sir, so if the channel is not present, then only one.
Yes, in the absence of channel charge, we call it cutoff. In the presence of channel charge, it's on. Yes.
Not saturation.
So,
No, cutoff doesn't mean not saturation. Cutoff means off. So cutoff means this. Right? But note that when VGS is greater than VTH, it doesn't necessarily mean that IDS equal to 0. IDS is greater than 0. This is an example of this, right?
For saturation, we want that VDS more than VGS.
Correct. Yes.
Then how do we show that it's more than 1 volt?
We don't show that. I'm not saying that this is. I'm not saying this is in saturation. All I'm saying is that this is not in. It's not in. It's not in the state where VGS is less than VTH. You have channel charge. Now, if its transistor is on, it can go in either one of those two regions. It can be either linear or saturation.
It depends on VDS.
Which depends on VDS. Now, if you set it up like this, naturally you don't have anything connected to the drain, right? So if, I mean, for the sake of visualizing, assume that there's a small capacitor. Okay. We are not particularly good in dealing with open circuits. So assume that we have a small capacitor. So what do you think will be the voltage on the top plate of the capacitor if we set it up like this? Why will it be VGSQ minus VTH? I had an uncharged capacitor connected there initially, right? So then what will happen? Okay, so let's assume that you have I mean, we can do this contradiction theory, right? So let's assume you had 2 volts on this. You had some charge on this plate of the capacitor to start off, right? Initially, you had some charge on this capacitor, you had 2 volts on this, and you set it up like this. Whatever you have, what do you think will happen to that charge?
It will start to dissipate.
It will start to discharge, right? Because the transistor is on, right? So it is equivalent to saying that you had a capacitor here, you had some charge here, and this was 2 volt, this was 0, and this is connected to 2 volt. So you have an electric field. You have an electric field through an on channel. The charge will flow, right? Charge will flow. So this capacitor will discharge, and it will discharge till. It will discharge till 0. So essentially, at steady state, this will go to 0 volt. So this is 0. This is 0. VGS is high. Which region of operation this is at?
Linear.
It's in linear because VDS is equal to 0 volt. VGS is equal to 2 volt. So clearly, your VDS is less than VGS minus VTH. Okay, so this is drain. This is source. So do you agree with the fact that the capacitor will discharge? You don't agree or agree? Okay, so if the capacitor discharges, then the voltage on the drain goes to 0. Right? If the voltage on the drain goes to 0, source is hard grounded, which means VDS is 0. If VDS is 0, then obviously with these conditions, you see that we are in linear region. Note that linear region of operation doesn't necessarily mean that you need to have a current. You can get into, as long as the transistor is on and you are satisfied, you are You are satisfying this condition, you are in linear region. Okay, this is a classic example of that. Make sense?
Originally,
Yes.
originally VDS was 2 volt.
Initially, when you started off, it was 2 volt. Then you let let the system settle. Initially, it was in saturation. Good point.
But
Yes.
that means that MOSFET was not acting like a resistor.
Yes.
So it might be the case that the capacitor did not discharge.
Okay. Good question. So here's actually that's the correct question. So let's assume this. So let's say when you started off, right? When you started off at t equal to 0, this was at 2 volt, and at this particular situation, what is the condition of operation? It's in saturation because your VDS is 2 volt, VDS is 2 volt, and VGS is 2 volt minus threshold voltage is 1 volt. So clearly this is this, right? So it's in saturation. So in saturation, what if it's a transistor in saturation, will you have a current flow or not?
Yes.
You'll have a current flow, right? And the current flow equation is half mu C of VGS minus VT whole square. So there will be a current flow. When you have a current flow, which means the cap is discharging, right? So it will discharge till what value? Till how long will it remain in saturation? Till what value of VD? Till VD of 1 volt, this transistor will remain in saturation, right? So it starts from maybe 2 volt. Then, if I sketch this, let's say this is VDS, and let's say it's time. Okay. So you started off with VDS of 2 volt, then it will discharge. What will be the discharge profile? I know that this will decrease. I know this will decrease. It can decrease like this. It can decrease like this. What will it, how will the discharge profile look like?
So it would like the discharge constantly till 1 volt because the IDS is.
Okay, good point. What he is trying to say is that, see, I mean, this IDS current is dependent on VGS in saturation. It's not dependent on VDS. It's a constant current source. When it's discharging, it's equivalent to saying that I have a constant current source of value mu C ox W by L VGS minus VT whole square. No dependence on VDS. It's a constant current source. You are taking current off the capacitor at a constant rate, which means the voltage will go down linearly. And it will go down linearly till VDS equal to 1 volt. Because after current on VDS, because you are going into linear region of operation, right? So now, if had that been a pure resistor, I could have said time constant and it goes down with all those things. But now it's not an exact resistor. So you will see some profile. You will see some profile, but this profile will not be exactly equal to a first order discharge, right? So maybe it goes like this, and eventually it will go to 0. Asymptotically, it will go to 0. So at steady state, your VDS will become 0, right? Okay, you had a question? Okay, fine. So now let's resume our endeavor to make an amplifier. Okay, so we have to keep the drain at a voltage of at least greater than 1 volt, right? Because VGS is 2 volts, threshold voltage is 1 volt. Yes. It will not be exponential, definitely. It will 0, but why will you say it's not exponential or asymptotic? Correct. Why do you say so? But its quadratic variation is not for, I mean, when you go to very small values of VDS, right? When you go to very small values of VDS, what is happening? What is the other equation? Okay. So you can say that I can neglect this term. It's behave as it loses, as the capacitor keeps on losing charge, the transistor becomes more and more resistive. So essentially, it becomes asymptotic because at very small values of VDS, it behaves like a resistor. Right? Yes.
Can't we directly give the VGS voltage to the source terminal?
Can't we give the? I didn't understand the question fully. Okay.
From the positive terminal of VGS, we can connect the source terminal, 3 terminal.
Okay, right. Okay, so if I understand correctly, what you are saying is, why don't we connect this to that, right? Yes, we can. And that in fact is a very useful circuit. We'll come to that. But as it turns out, that cannot be used as an amplifier. Again, we'll come to that later on. Not yes, it will always remain in saturation. Correct. But let's assume you have another voltage source. You had a question, some idea? No? Okay, fine. So now we have to keep it in saturation, which means we agree on the fact that on the drain voltage has to be at least 1 volt or more. Okay. So what do? I connect a battery VDS, which is equal to, let's say, 2 volt. Okay. Safely in saturation. This is the point that he was trying to make also. Why don't we connect this to that? This is equivalent to saying I have VGS also 2 volt, VDS is also 2 volt. Fine. So now what we need, this is biased in saturation, no problem. But only biasing is not enough. We have to apply an input, right? We need an amplifier, so which means we have an input and we need to connect this contraption to a RL. Okay. So how do I connect an input now? Note that I have to connect the input between gate and source. Right?
Incremental for the incremental analysis.
Forget about analysis will come after synthesis, right? After you make the circuit, after you design, then you do analysis. So how do you design? So how do you apply an input?
In the 201, there was one capacitor.
Okay, so why do you need a capacitor? Okay, forget about capacitor. I mean, let's start. I mean, in the absence of, I mean, this is one of those principles of engineering that in the absence of any information, the simplest solution is the best solution, right? So you will see that throughout engineering design, right? So what is the simplest thing that you can think of right now? Directly connect, right? So let's directly connect. So do you see an issue if I directly connect? What is the issue?
Backflow.
What do you mean by backflow of current?
Part will get into the RF.
Okay, but I agree with what you were saying, but is there an even greater concern? What do I expect? I am expecting the incremental voltage VI that I'm applying should appear fully across the gate, right? So note that in the incremental sense, I want this. So this should be gate, this is source, and these are connected, right? This is drain. In the incremental sense, I want this. So do you think in the incremental sense, the actual circuit will behave like what we want?
So basically there is no application because connected it directly, you can use the DC battery directly.
Correct, exactly, right? So what is pointing out is the fact that, see, in the incremental sense, this is shorted, right? I have a DC source connected between gate and source, right? And even if you don't go into the incremental sense, what is it telling you? It is essentially telling you that whatever you do anywhere in the circuit, you will not be able to change the gate to source voltage because I have a constant battery. I have a constant battery connected between gate and source, which means I'll not be able to change the voltage between gate and source by applying whatever VI and whatever I want to do here, right? So which means, which in an incremental parlance means that gate to source is shorted. Okay, so we cannot do this. So what else can we do? Connected in series, great, right? So what she is pointing out is that why should we limit ourselves by connecting in parallel? Ultimately, we would want what we want. Ultimately, we want an increment on top of whatever we have, right? We want the transistor to be in saturation. We want the transistor to be on all the time. But on top of that, I want the increment, right? So why am I saying that? So note that, let me go back to the Taylor series equivalent again. So your IDS is mu n Cox. Okay. So why don't you tell me why do you think this will work?
Is this infinite current in the?
No infinite current. Why should you have infinite current? So I am interested in VGS, right? I am interested. What am I interested in the incremental sense? What am I interested in? So forget about this entire stuff here. Let me redraw only the stuff on the left, which means I have VI, RS, VGSQ, which is 2 volt, and I'm interested in these voltages. So that voltage is always VGSQ.
Okay, so basically
Here doesn't matter. That's all it means. Right? But what do I want? I want the voltage VGS to be, I want the total voltage VGS to be VGSQ plus VI. This is I want, right? And why do you want this? I mean, if we, to refresh your memory, your current equation is now if I apply, this is the quiescent. This is quiescent, right? VGSQ. This is quiescent. Now, if I apply a small increment on VGSQ, right? So if I apply a small increment on VGSQ, what will happen? So your total ID will be right? So if I expand this and I club these two terms together, I will get what? I will get some plus that cross product term. Recall we wanted that cross product, right? Amplification required that cross product, right? So correct. So this IDS was, I can say, is incremental IDS plus the quiescent IDS. This quiescent IDS, this goes, and you are left with the other terms, which is IDS, which is equal to, this is the linear term, right? This is the linear term with respect to VI. And can you look into your notes and tell me what is this quantity? This is Y21 or GM. It's a transconductance, right? So this is GM times VI plus some additional term. Correct? Under small signal approximation, oh, sorry, I missed one term. Did I miss? No. Okay. Under small signal approximation, we are essentially saying that we are applying that value of VI for which only this term will suffice. Okay, that's essentially I mean, in a nutshell, this is what a small signal approximation is, and we are saying that this will be much lesser than GM times VI, so I can neglect that. So we are limiting ourselves and saying that we will be applying that value of VI for which this is true. Now, if this is true, where am I applying this VI to? I am applying this VI on top of VGS, on top of VGSQ, right? I am applying VI on top of VGSQ, which means I am applying a series voltage. Okay, so now how do you now set up your circuit for a series voltage condition? You simply say that I have this VGSQ and I apply VI here. Right? Make sense? So now, what do you think will be the total voltage at the gate or between the gate and the source? It will be equal to 2 volt plus 2 volt plus Vi. It's no longer clamped to 2 volts. Your Vi can move, right? Your gate to source voltage can move. So the first objective is served, right? Make sense? So if I have this, what will be the total current flowing through the MOSFET? Total current is quiescent plus incremental, right? What was the quiescent current? It was some IDSQ plus incremental. What is the incremental current? GM times Vi, right? It's GM times Vi. The incremental current is GM times Vi. So this is the total incremental current. But where is this total incremental current going into? It's going into a voltage source, which means I don't have any incremental output voltage. Output is again clamped. Okay, so what is the voltage between drain and source? Clamped at 2 volts, right? I have applied a constant voltage. It's clamped at 2 volts, it cannot move. I have an incremental current, but it cannot generate an incremental voltage, right? In a small signal parlance, again, in the small signal parlance, if I have to sketch the small signal equivalent of whatever I have sketched here, what will I do? I will look firstly, I'll replace this transistor with its incremental equivalent. So this is gate source. This is GM times VGS. And this is the drain. Looking on the input side, what will I do? I will replace the gate VGSQ constant voltage sources with a short circuit, right? Do you agree? Constant voltage sources in incremental sense goes to short. The resistor remains as is, and this is the incremental input Vi. At the output side, the constant voltage source VDS becomes a short circuit. So even though I have an incremental current, it's not able to generate any incremental voltage. And also note that this is also not sufficient. We need to deliver power to some RL, right? Ultimately, that's the goal. I have some RL somewhere, and I need to develop, I need to push this current into RL, which means this current, whatever this current I have, has to go into RL. It cannot go into this short. So how, now the next question is, how do I arrange that? I have an RL. How do I plug it into my total MOSFET circuit to develop that? In series with the battery, right? So just to ensure that everybody is in the same page, what happens if I connect it like this? It becomes shorted again, right? A voltage across RL is again clamped to 2 volts, right? So great, I can apply this in series with the battery. So now do you think this will, I mean, let's assume RL equal to some 10K. Okay, let's say RL equal to 10K, let's take some values, okay? So let's say mu n Cox W over L is 1 milliamp per volt square. By the way, W by L is also a design handle. We'll get to that later. Let's assume that mu n Cox W by L is 2 milliamps per volt square. Okay. So do you think this has, if I plug in RL the way we have here, it will work, or is there an issue? There is an issue. What is the issue?
Like 20 amperes DC current is flowing.
Okay. So how do you get to 20 amperes of DC current?
When C of W by L, VGS minus.
Okay. So under quiescent condition, right? Under quiescent condition, what again? When you change anything in the circuit, you have to go back to see whether your quiescent has gotten disturbed or not. Right? So if the quiescent has gotten disturbed, again your small signal model will get disturbed. So any change, go back to quiescent and check your quiescent isn't disturbed. So now we have to check whether the quiescent has gotten disturbed or not. So how do I check? What am I looking for? I'm looking for whether I definitely know that the VGS hasn't gotten disturbed, but the VDS has a possibility of getting disturbed. Right? So initially VDS was 2 volt, but now I have source is at grounded, but the drain would have been at lower voltage than 2 volt. because I am drawing current through the resistor from the battery. Okay, so the drain is no longer connected to a fixed voltage of 2 volt, right? So which means that I have to establish what is that voltage now. So when you have any nonlinear device, how do you go about doing that? You assume that I am in a certain regime of operation. Let's assume that, go ahead and see whether it's valid or not, right? So let's assume, to start off, this is a saturation region of operation. If it is in saturation region of operation, what will my IDSQ be? So assume saturation. So your IDSQ will be half of mu n Cox W by L times VGSQ minus threshold voltage whole square. So this is 2 milliamps, means this is 1 milli, times this is 2 minus 1 is 1, which means you have 1 milliamp flowing through the transistor. This is assuming saturation region of operation. Now, if 1 milliamp flows through this battery, through this transistor, which means this 1 milliamp is also flowing through the resistor. And one side of the resistor is at 2 volt. So what will this voltage be? 2 volt minus 1 milliamp times the resistor, which means this is 2 minus 1 times 10, which is minus 8. So clearly, it's a non-sustainable situation, right? So the transistor will definitely not be in saturation. It will go into triode, and when it goes into triode, you cannot use this equation. You have to use a triode region equation to figure out what will the actual voltage be. But that is beyond what we want, right? We want to just establish whether it's in saturation or not. So this gives you the handle that this is not in saturation. Okay, so what can I do to ensure that this is in saturation? Let's assume you can play around with the batteries for timing. You can change battery voltages, let's assume. So is there something that you can do to ensure that this thing is in saturation? I can adjust VDS. I can increase VDS such that this voltage, the drain voltage, moves up, right? So assuming it's a constant current that I am drawing, I'm assuming that it's a constant current that I am drawing through the MOSFET, I know exactly how much I need to increase the VDS by, right? So how much should I increase the VDS by? What? I have to increase the VDS by not only plus 8 volts, right?
Plus 9.
Yeah, so I see plus 8, plus 9. So anybody from back, anybody want to volunteer? The question is, do you agree with the fact that the transistor is not in saturation? So there was one proposal that I can change VDS, right? I can change this applied battery voltage to increase. Now I should not call it VDS, by the way. There should be some VDD, because it's no longer connected between drain and source, right? So if I increase VDD, there's a likelihood that I will get the transistor, I can go back into saturation. So if we buy that argument, then my question is, how much should I increase VDD by? I have to increase it by 9 volt, because if I increase it by 8 volt, and this goes to 10 volts, then the voltage here, voltage at the drain will be minus 8 volt plus 8 volt, which is 0, right? But 0 is not sufficient, because how much do I want? How much do I want the drain voltage to be? At least I want it to be plus 1 volt, right? Because note again that for saturation region, we have to ensure that VDS is greater than equal to VGS minus VTH. In this case, your VGS is 2 volt. This is 1 volt. So which means this has to be greater than 1 volt, right? So drain of the transistor has to be at least equal to 1 volt, because source is grounded. Okay. So in other words, I'll have to increase the VDD to 9 volts, additional 1 volt, right? So in other words, if I redraw, this is what I would expect it to be.
Just we are increasing this voltage in the parent circuit
Correct.
before adding the VI, VR.
Yes, correct. This current was 1 milliamps because that's how we had set it up under condition of this is as for saturation, right? For sat. So if this is the case, I know that this voltage will be at least be equal to 1 volt, and we are in safely into saturation region of operation. So now if I observe, the voltage across RL, right? So what will I observe if this is VI? Right, what will be the total current? Total current still is 1 milliamp plus GM times VI, right? So what will be the total voltage drop across RL? Let me call this VRL. What will be VRL? Total voltage drop.
10 volt plus.
10 volt plus will be plus or minus? Why minus? Okay, plus or minus. Okay, so why plus, why minus? Why was it minus? Why I heard some minus somewhere. It's the way I have marked VRL, right? It's the way I have marked VRL, right? So I am pulling current out. It's the way I have marked this will VRL will be GM times VI times RL, right? So out of which, since this VRL I can say as VRLQ plus some small VRL, right? So with this VRLQ, this goes. So your VRL will be GM times RL times VI, which means the relationship between the voltage across RL and VI is GM times RL. And if you can ensure that GM times RL is greater than 1, if you can ensure that, right, then you have amplification, right? So what is the GM here? GM is can easily figure out from whatever I have parameters that I have given, right? GM is mu n Cox W by L VGS Q minus threshold voltage. This is 2 milliamps. This is 1, which means 2 millisiemens. And this is 2 millisiemens times 10K, which is 20. Right? So you'll be able to, you are essentially seeing 20 times increase in activity, right? You have 20 times increase in the volt in VI at the output, right? So you have an amplifier of value of gain of 20. Okay.
Basically, we have to take an assumption, and if it is in saturation, then we're getting an.
Correct.